Well, hello, PreCal. Here we are again. Wish I was there with you, but we're having to make do under the circumstances. So here we are. We're in the middle of Chapter 6 together, and today we're going to be looking at Section 4. This is actually the second half of Chapter 6. Chapter 6 is kind of broken into the vectors in Sections 1, 2, and 3, and now in Sections 4, 5, and 6 we're going to be talking about polar coordinates. Now you've already learned the Cartesian plane. It looks like this, right? Where we could identify the location of any point on the plane with an ordered pair, x comma y. For example, this point you'd be able to tell me was 1 comma 3, right? 1 in the x direction, 3 in the y direction. Or if I gave you the point -2, 4, you could go -2 over and then 4 up, and you'd find a point somewhere around there. And you could label that for us. Well, today we're going to be talking about polar coordinates. And that's what 6.4 is entitled. Now, you've seen polar coordinates before, most notably with radar applications like this, right? Where you usually will see some sort of like line like this that's like sweeping around here. And every time it sweeps around and it has a point of contact, you get a glowing dot, right? And it keeps track of each of these points of contact. And the measurement of this is done from a pole, from a center point, the distance out from that pole to the points of contact, and then combined with a degree measurement of how far away we've swept around and how far out it is from there. So in polar coordinates, we can describe position with just a distance and an angle direction. Remember, with the xy plane, we would give an x coordinate and a y coordinate and find the dot. But here with polar coordinates, all we're interested in is a distance out from the pole and an angle measurement, theta, away from the polar axis. The polar axis is along the x-axis in the positive direction. That's considered like 0 degrees. And so then we travel counterclockwise around for theta. If you travel the other way, it just becomes negative theta. Okay. Now, polar grids can be measured in degrees or radians. So in this particular example, we see that from 0 degrees here to 90 degrees, we split it into 1, 2, 3, 4, 5, 6 pieces. So 90 divided by 6 is 15 degrees. Or we also know that as pi over 12. Remember, going all the way from here to here would be 1 pi. And so this has been split into 12 sections. So it'll be pi over 12 for just this amount, or 15 degrees. So just make sure that you're careful about degree measurements or radians. You'll find both radians and degree measurements in the problems ahead. So if you're using your calculator, just make sure that you're in the right mode whenever you're doing trigonomic functions of these things. Make sure you're in radians if it's something like pi over 12. Make sure that you're in degree mode if it's 15 degrees. So in example 1, it's just asking us to graph each point. So let's graph point A. So the way that you do this, normally you're used to looking at the first number first, like the x comma y. But here, remember, we have an r comma theta. And I think it's easier actually to first find the theta, find the angle, and then count out the number for the radius out from the pole. So in this case, we would find pi over 3. And pi over 3 would be located right here. Remember, these are each pi over 12 each. So we would need 4 pi over 12. So 1, 2, 3, 4 gets us to 4 pi over 12, right? And 4 pi over 12 is the same thing as pi over 3. And then we would just measure out 3 units. Remember, now the units are going to look like circles because it's just a radius away from the center pole. So we just go 1, 2, 3, 4, and we make a dot out here at 4 comma pi over 3. And it's that simple. Example B says, find point B, which is at 2 comma negative 120. Now notice that this is a negative degree measurement. Remember, these are in 15 degree measurements here. So we're just going to go around this direction. This will be 90 once we get to here. Another 15 would be 105. Another 15 would be 120. So we need it along this line here. And we need it out 2. So 1, 2. So it should be located, B should be sitting right about there. If we're to ask us to graph point C, now notice what's happened. We've got a negative in the radius. This is also workable for us. So first of all, remember, let's do the 3 pi over 4. So 1 pi would be all the way over here. So we're looking at halfway between that and pi over 2. So it would be right along this line. But notice it's negative. Well, all we do then is we just count in the opposite direction along that same line. And we go 1, 2, 3. And we make a point down here. And that would be point C. All right, now I just want to mention here that with any point, remember whenever we're talking about going around, when you have degree measurements like this, you can get to coterminal angles. So for any point r comma theta, we can add n times 2 pi and come to the same measurement, right? So if here I've got the circle around, notice if this was my degree measurement here, if theta was sitting right here, well, if I add 2 pi to that, I go all the way around and back to the same angle. So that point can be represented by that amount of degrees or pi radians times plus 2 pi, plus any number of 2 pi. We can keep coming around as long as we come back to that exact same line. But it's also true that if we look at it in the negative direction, we can also get at that same point, because we could also have this degree measurement, but then have a negative number, which would then push us again up here again. So we can also do the point negative r and then have theta plus or minus pi. Because remember, we can, from this direction, if we go plus or minus, plus pi or minus pi, we get to get the same angle if the radius is negative. That would make it direct up this way. So we could also say the point is negative r theta or plus 2n plus 1 times pi. Now that's a whole lot of a lot of numbers and stuff. Let me show you examples just to show you what we're talking about. I think it will become quite simple. So plot the point P, 3, 30 degrees, and state 4 additional pairs of polar coordinates for P. So here's P at 3, 30 degrees. So we're going to state 4 additional pairs. Well, the first one could just be, well, let's just go all the way around another 360 degrees. So if we come up 30, we just going to go all the way around again. So what's 30 plus 360? Well, 30 plus 360 is 390. So we could also represent that point as 3, 390 degrees. What if we went in the opposite direction with measuring the theta? We could also measure, remember, in the negative direction in theta. And that would just mean if this was 30 here, then it would be just 360 minus that 30. Or better said, 30 minus the 360, which would get us to negative 330 degrees. So that would also represent that same thing. Now we could just keep adding, 2 pi or 360. Just keep adding 360 and get all of our 4 different ones. But how about instead we do it the other way, where we give a negative measurement for the radius? Well, we could then say, instead of it being 30 degrees, we could add 180 to that 30 and get 210 degrees. And then just, instead of doing 3 in the positive direction, make it a radius in the negative direction, negative 3, 210. And if we can measure that angle from this direction, we could also measure it from this direction. And in this direction, remember, going from here, the x equals 0 line, we would get negative 150. Again, if this is 30, then it has to be 180 to make a straight line there. So this must be negative 150. And then again, instead of having positive 3, we'll do negative 3, which makes it up at that same point. So that's 4 different ways to represent the exact same point on the polar plane. All right, now what we have here is just kind of showing you, if we're wanting to convert from the Cartesian plane, from an xy plane to polar coordinates, what we've done here is just impose the polar coordinate system on top of the Cartesian one. So we see here the x-axis and the y-axis, but we also see these circles, which are reminding us of the polar plane. Note here that we can represent a point P as being just r comma theta. We can also represent it as the point x comma y. Well, once we have all of that together, we know that's the exact same point. We can then say a couple of things. First of all, we can say that the length of r is, by the Pythagorean theorem, right, because this is a right triangle, x squared plus y squared, take the square root of that. Like r squared equals x squared plus y squared. So r must be the square root of x squared plus r squared. We also know that theta we know the trigonomic ratios, right? Cosine of theta is going to be x over r. Sine of theta is going to be y, opposite, right, over hypotenuse, y over r. And we also know tangent of theta is y over x. Now, with these four formulas, we can then convert from polar coordinates to Cartesian, and we can convert from Cartesian coordinates to polar. So we're going to get some examples doing that. We can rewrite this as x equals r times cosine theta, or y equals r sine theta, right? Just by multiplying this r up in both cases, we can get x or y by themselves. So if we were asked to convert the polar coordinates 2, 2 pi over 3 to rectangular coordinates, what would we do? Well, remember that x, y, we just rewrite x and y as r cosine theta and r sine theta. So remember, the x coordinate is just r times cosine theta. Remember, if we have some point P here, and this is r, and we know this is theta, well, the x component down here is just going to be r cosine theta, and the y component over here is going to be r sine theta. So we just plug in the numbers then. 2 times cosine of 2 pi over 3, 2 times sine of 2 pi over 3. This is just easy trig, right? Which is just 2 times the negative 1/2, or 2 times the square root of 3 over 2. Or again, if you're putting in a calculator, you could get approximates. -1, there's -1, square root of 3. Or we can get in calculator -1, 1.73. All right, how about this one? Find the polar coordinates for P, which is -5, -12, where r is greater than 0 and theta is 0, between 0 and 360 degrees. Remember, there's several different ways that we can get the theta measurement. What do we do here? Well, we can just set up again our triangle. Remember, this point is -5, -12, so this is -5, and this is -12. So how do we find r? Well, we have from our previous equation, r squared equals x squared plus y squared. So x squared is 5 squared is 25, 12 squared is 144, 144 plus 25 is 169. And the square root of 169 is plus or minus 13. Now notice, it can be plus or minus because it could be a minus if we took the theta being this direction. But we're already told that r is greater than 0. So we're going to take the positive one. We're going to take r equals 13. And now how do we find out what this theta measurement is? Well, we can make use of finding what this reference angle is first, this reference angle alpha. Well, the angle alpha, we know that tangent, right, of alpha is going to be what? It'd be opposite -12 over -5. -12 over -5 is the arc tangent then of that. We just take the arc tangent, right, of that to find alpha. We get 67.4. Remember, that's the measurement for alpha. We need the measurement for theta, which goes all the way around to here. So all we have to do is add 180 to that. And we get our final answer of 13, 247.4 degrees. Remember on all of these things, make sure that you are in the right mode. If we're doing with degrees, make sure you're in degree mode. If it changes over to pi radians and stuff like that, you need to be in radian mode. So why don't you work this one on your own? Pause the video here. Whoever's there subbing for me, why don't you just even pause the video and you guys try to work this one out. Convert 6, 120 to rectangular coordinates. Pause the video now and see if you can work this out. Okay, so I'm going to assume you went ahead and paused it, and you actually are doing this the way I've asked you to. So, remember, our coordinates are just x, y, which would be r cosine theta, r sine theta. And now we just plug in the numbers. It'd be 6 times cosine 120, and then 6 times sine of 120. And when you do that, you should get -3 and 3 square roots of 3, or in approximates, if you put it in a calculator, -3, 5.196. How about this one? Pause the video again. Convert 6, -7 to polar coordinates, where theta has to be between 0 and 360 degrees. Okay, pause the video. See if you can work this. All right. So again, I think it's best on these ones to start with a picture. So 6, -7, would be right there. We can draw ourselves a triangle. And from that, we can now use our equations. R squared equals x squared plus y squared, which in this case is the square root of 85 for r, which is approximately 9.22. And then from that, we can again do arctangent of -7 over 6. The reason I have the absolute value here is because we want to make sure we get a positive value. We're just looking for what this alpha is going to be, and then we will think about where that's positioned and make the appropriate adjustment for whatever we need to do. But in this case, we get an answer of 49.4. Now notice that's what alpha would be. So if that's going down this direction, we have to indicate that that's a negative degree measurement. Or we can do it from the positive way, because it's been asked between 0 and 360. So we'd have to do 360 minus that, which gives us to 310.6. So our final answer is the square root of 85, or approximately 9.22, and 310.6 degrees. All right, now this section also introduces the polar distance formula, which is this: d equals r1 squared plus r2 squared minus 2 times r1 r2 times cosine of theta 2 minus theta 1, all of that under the square root. Now, if you're looking at this and you remember from the previous chapter we had that this looks like the law of cosines, there's good reason why it looks like the law of cosines. It really does. It pretty much is that. And we'll see in this next example why that is. So the radar on a battleship detects ships, one of them at 15 miles at 140 degrees, another one 27 miles at 240 degrees. Find the distance between the two ships. So notice that the radar or the battleship, it's helpful for that battleship to know where each one of them are in reference to itself. But what if those two ships want to know how far away they are from one another? So how would they go about doing this? Well, let's draw a little picture here. Notice that here's the radar. Here we have the two ships being represented. The first one was 15 miles at 140 degrees, the other one at 27 at 240 degrees. And so now, by the distance formula that we just had, all we do is plug in each of these things. Notice what we have. We have a measurement of a side, and a measurement of a side, and we have an angle. We have side, angle, side, which is prime for the law of cosines. So this is the law of cosines being utilized to find the distance of d here. So then we just plug in all of the numbers. And when you do, if you've done it correctly, you should get an answer of roughly 33.1 miles. So go ahead and try to put that in your calculator. Put in all the numbers, right? So this should be 15 here. It should be 27 here. 15, 27. And then here, this theta 2, remember, has to be the measurement of this minus the measurement of this. So make sure that you do those measurements rightly. But when you do all of that, make sure you're in degree mode, you should get an answer of 33.1 miles. Exercise 23 on page 313 in your book asks you to find the distance between the polar coordinates 3 comma pi over 3 and -1 comma pi over 2 to the nearest tenth. Notice here that we've changed to radians, so make sure that you're in radian mode. This is going to be, I keep stressing this because this is where you could get things wrong, is if you just have your calculator in the wrong mode when you're doing the calculations. But otherwise, we're just plugging it into the distance formula. So we're going to do 3 squared plus -1 squared minus 2 times 3 times -1 times cosine of pi halves minus pi over 3. And when you do all of that, you should get an answer of 3.9. So again, try to do that in your calculator. Make sure that you get an answer of 3.9. If you need to pause the video, do that here. Make sure that you can get to that right answer. All right, so we have these 3 equations that are so helpful to us. R squared equals x squared plus y squared. Cosine theta equals x over r. Sine theta equals y over r. We could also include in this tangent of theta equals y over x. That one's also sometimes useful. So you're going to use all of these in the following problems to move from polar to Cartesian or Cartesian to polar coordinates. And sometimes we have to do a little bit of tricks with it. So I'm going to show you some examples of that. Write the equation of the line x equals 2 in polar form where r is expressed in terms of theta. Okay, now you're going to be able to verify this in your calculator itself if you change the mode on the TI-84 to polar. So I'll let you see this in a second. But remember, x equals 2 if we were going to look at that in our Cartesian plane, we would just say x2 is right here. Remember, x equals 2 would just be a vertical line. So we're trying to convert x equals 2 to polar form. Well, how do we go about doing that? Well, let's look at the several equations that we had on the previous slide and think through which one we want to use here. Well, look at what we've got. We have x equals 2. Well, we have this equation, cosine theta equals x over r, or x equals r cosine theta, right? So wherever we see an x, we can just write r cosine theta. So r cosine theta equals 2. And now we just solve for r. R equals 2 over cosine theta, which remember, 1 over cosine is the same as secant. So we could rewrite this as r equals 2 secant theta. Now, on your calculators, you guys can try this out. If you change the mode, go to your mode and make sure that you're in polar mode. After you've done that, if you click the y equals key up at the top left on your graphing calculator, you should see a mode now where you're seeing r values. And all you have to do is, on the first one, just write 2 divided by cosine theta. And when you then go to graph that, you should see a vertical line straight up and down about where x equals 2 exists. All right, on page 313, exercise 27, it says 2x minus y equals 4. So we're to convert this into polar form. So how do we go about doing that? Well, remember, we have x equals r cosine theta and y equals r sine theta. So we can just plug those in. 2r cosine theta minus r sine theta equals 4. And now for solving for r, all we have to do is pull the r out of this, factor an r out, and then divide by the stuff that's left. So we factor out an r, and we're left with 2 cosine theta minus sine theta, and then we divide by all of that. And we get r equals 4 over 2 cosine theta minus sine theta. And again, if you type all of that into your TI-84 while you're in polar mode, you should get something that looks like, remember, this is pretty much just a line, right? We could rewrite that as y equals 2x minus 4. So it should have a y-intercept of -4, and then it should go up 2 over 1, up 2 over 1. So it should intercept the x-axis at 2 and look something like that. It should be a line like that. And it will look like that. If you're in polar mode and you type this in, you should get a straight line on that graph. You can try that out, see if you get it. Okay, on example 7, on page 312, it says, write each equation in rectangular form and describe its graph. So the first one says r equals 3. So let's think about that for a moment. If we're in polar mode and we have a radius of 3, what does that mean? Well, it means from the origin, if we go out 3 in any direction, we can go out 3 in any direction, that's the place where we should be, which would just be like making a circle, right? So this should look like a circle when we're done with it. Well, you might be able to remember that the equation of a circle is x squared plus y squared equals r squared. But if you don't remember that, we can just, again, look at our equations that we had. And we had these equations. R squared equals x squared plus y squared, cosine theta equals x over r, sine theta equals y over r. Well, we have no theta that's given to us here. So we kind of already know that these two must not be used in this one. So we have to use this guy. So probably the easiest way to do this would be to say, well, if r equals 3, we want to make this say r squared equals something. Well, if I want to square both sides, what would the answer be? Well, if I square both sides, it would be r squared equals 9, right? Because 3 squared would be 9. And now I have an r squared. And for the r squared, I can now plug in x squared plus y squared. And get x squared plus y squared equals 9. And that is the equation of a circle centered at the origin with a radius of 3. What about this one? It says write equation for this in rectangular form if we have the polar equation being theta equals pi over 6. Let's think about what that means. Theta equals pi over 6. So if we were to go up pi over 6, which is like 30 degrees, right? That's saying that theta equals pi over 6, which would be the line at pi over 6. Well, now let's, again, use the equations that we have. We have tangent theta equals y over x. That's going to be the one we want to use because the other ones, remember, have r's in them, and we have no r in this. We only have a theta. So this is actually the equation we want to use. Tangent theta equals y over x. Well, that means we just have to rewrite this one. Instead of that being just theta equals pi over 6, let's take the tangent of both sides. Tangent of theta equals tangent of pi over 6. And now wherever I see tangent theta, I can plug in a y over x. And so we plug that in. Y over x equals tangent of pi over 6. And if you remember tangent of pi over 6, it's just the square root of 3 over 3. And now we can cross multiply, or just multiply the x up, actually, because we just want y by itself. And we get y equals the square root of 3 over 3x. And again, if you look at that, that's going to be this exact line. So we get the same thing in then the rectangular form, which is what we were after in the first place. Notice here that it would just be a line at theta equals pi over 6, or a slope of pi over, or square root of 3 over 3, with the y-intercept at 0 and x-intercept at 0. It's passing through the origin. All right, one more example. It says, write r equals 4 sine theta in rectangular form. So r sine theta in rectangular form. Well, okay. So we just, first of all, I think the best thing to do here is just multiply both sides by r. Why? Because we have a conversion for r squared. Remember, r squared equals x squared plus y squared. So we just plug in x squared plus y squared for where there was an r squared. And on this side, remember, r sine theta is y. So we just plug in y for r sine theta. And then we can subtract the 4y over. And if we want to get this in like standard form of what this does, what you have to do with this part is to complete the square. Again, if you got this far, you've already got it, pretty good. But if we want to complete it all the way to the standard form, we would complete the square of this. Now, if you remember how you do that, you take half of this guy and then square it. So it looks like this. It's going to be x squared plus y squared minus 4y plus 4, because half of that squared is 4. And then we have to add a 4 to the other side in order to keep the equation balanced. And we do that so we could rewrite this middle thing as y minus 2 squared. And then we would rewrite, so this is the final answer, x squared plus y minus 2, quantity squared equals 4. And that will give us the picture of a circle whose center is at 0, 2 with a radius of 2. It should look just like this. The center is at 0, 2 with a radius of 2 going all the way around. Again, if you put this into your calculator in polar mode, you would get this circle. Or if you did it with the previous equation of solving for y, you could get, again, the same circle. One other thing, on page 314, exercise 40, it asks you, this is just a good example to just kind of show you some tips of how you go about these. It says transform x minus 2 squared plus y plus 1 squared equals 5 into polar form. Well, you could start off by just going like, oh, well, I remember that x equals r cosine theta and y equals r sine theta. But in this case, it might be actually quicker if you just go ahead and square out these, you FOIL both of these parts to start. So if instead of that, I just write here x squared minus 4x plus 4, that's this part FOILed. And then the second part FOILed would be y squared plus 2y plus 1 equals 5. Now combine like terms, and notice that the 4 and the 1 and the 5, they cancel out, right? This would be 5 on both sides, so it just falls away. And we're left with x squared plus y squared equals 4x minus 2y. Now, notice x squared plus y squared, we know that that equals r squared. And now we plug in for x and y the r cosine theta and the r sine theta. And you get r squared equals 4r cosine theta minus 2r sine theta. Now all you have to do is divide everything by r. You get r by itself. And you get a final answer of r equals 4 cosine theta minus 2 sine theta. And you're done. I guess you could factor out a 2 and say 2 times the quantity of 2 cosine theta minus sine theta, but either of those answers would be totally acceptable. And we're done. Okay, so what I'm going to give you assigned for homework is to do 2 through 38 even, and then numbers 52 and 54. Those last couple are some cumulative review, but this is the new stuff that we were just doing. This week, just so you guys know, we're just going to be doing these 3 sections. So we have 6.4 and then 6.5 and 6.6. So you have 5 days in which to do 3 sections. So if you get bogged down anywhere along the way, I'm more than happy to help. If you guys want to reach out to me and want me to get on a Zoom call on one of these mornings, I'm happy to do that. I will record these 3 lessons, and if you guys want to work them Monday, Tuesday, Wednesday, and then Thursday, Friday, we can do Zoom calls, or if you want to break that up and do a Zoom call on Tuesday or Wednesday and another one on Thursday or Friday, I'm fine with that. But I'm here to help if you guys need any additional help. I know that sometimes doing it through video format, you don't get to interact with me as much. So, but at least the lesson is kind of there in front of you. Do the best that you can. Reach out to me. Let me know how it's going, and we'll get through this together. Thanks so much, guys. See you soon.